I'm just going to explain to you briefly what angular momentum is. And angular momentum is all to do with rotating bodies. So this could be a high board diver, it could be a gymnast, it could be a dancer, it could be a trampolinist. So we're looking at bodies that rotate around an axis of rotation. And whenever you're talking about rotation, you'll talk about the term angular momentum. So the two high board divers that have set off there, they will have applied something called a turning force called a torque. It's just a force that starts them spinning. So a torque is a turning force. So a dancer that spins or a gymnast that does a somersault, whoever it is that we're talking about, if they're spinning, if they're rotating, they have to have applied a turning force, a torque. And how much torque they apply dictates their overall angular momentum. So the greater the turning force that's applied, the greater their angular momentum will be. And angular momentum, if you're asked about it, is the quantity of motion that a rotating body possesses. So how much turning motion do those two high board divers have? It's made up of two factors. And again, any question on angular momentum needs our definition up here, but it also needs the fact that it's made up of two things: moment of inertia and multiplied by angular velocity. Now you'll notice with a high board diver, they've not got a lot of time in the air before they hit the water, but they do all sorts of things with the bodies, with their arms and the legs, to make sure that at some points they spin very quickly, so their angular velocity goes up, and other times they spin much slower in order to get a controlled entry into the water. So in a minute, I'm going to explain moment of inertia and angular velocity, and that will make a bit more sense to you. Let's have a little look at Tom Daly here. So he's obviously, set himself off with a spin. He's applied a torque, he's applied a turning force. And the other thing you need to know about angular momentum is once he's given himself that quantity of motion, that quantity of turning motion, his angular momentum remains constant. So again, you'll need to make sure that you put this into any question that you get. So just give me 1 minute. Angular momentum remains constant. So as soon as he started to spin and he's given himself a quantity of motion, that angular momentum remains constant. This is because we say that due to the mass of the body, the air resistance is negligible. So because it's a large mass, the air resistance, or a large weight force, the air resistance is considered to be negligible. We say that angular momentum has been conserved. And one of the reasons it's conserved is because when we spin fast, when angular velocity is high, our rate of rotation is high, our moment of inertia is low, and vice versa. So let's try and make a little bit more sense of that. So just before we move on, if you're asked a question linked to rotation and angular momentum, the key things that you're going to say are that we apply a turning force, a torque, that gives the body a quantity of turning or rotating motion. Angular momentum is made up of moment of inertia times angular velocity. Once we've started to spin, that angular momentum remains constant. This is because air resistance is negligible. We say that angular momentum has been conserved because the two things that it's made up of, angular velocity and moment of inertia, change. They've got an inverse relationship. When one of them is high, the other one is low. Let's try and make some sense of that now. So let's move this along here. Right, so you can see on the screen there to the right hand side, we've got a definition of angular velocity. So angular velocity is just the rate of rotation. How quickly is something spinning? Okay, and we can see on the two images that are on there on the board of our figure skater will be spinning quickly when everything's tucked in. So in this image here, her angular velocity, her rate of rotation is high because she's spinning fast. That gives her time to get in enough rotations. So her angular velocity, when everything's tucked in, is high. Remember, I said they had an inverse relationship. Now, moment of inertia, let me just show you across here, is something to do with the distribution of mass around the axes of rotation. So in other words, when her arms and her legs are out, so if we look at the figure skater here, her arms and her legs are away from this longitudinal axis of rotation, her moment of inertia is high. Moment of inertia is something to do with the resistance of a body to change its state of rotation. When her arms and her legs are out, she doesn't want to really rotate. So her moment of inertia is high, but we know it's got an inverse relationship, so her angular velocity is low. When she tucks everything in, so when she brings, and really learn these two kind of explanations here, when she brings a mass in her arms and her legs close to the axes of rotation, like this picture here, don't forget she's spinning around this longitudinal axis. When she brings everything close, her moment of inertia is low. She's quite happy to rotate at that moment in time, and her angular velocity is high. So if we just go back to this picture here and have a look with our figure skater, when her arms and legs are close to that axis of rotation, so she brings everything in close, she brings a mass, okay, or her arms and legs close to the axes, her moment of inertia is low, which means that she'll spin fast, her angular velocity is high. Look at it the other way, when she brings a mass, her arms and her legs away from this axis of rotation. So you can see the red circle there. Her mass is distributed away from the axis of rotation. Her moment of inertia is going to be high. She's reluctant to spin, and this slows her down. Her angular velocity is low. So what you need to be able to do in the exam is to look at the images that you've got, talk about the pictures that you've got. What is she doing with her arms and her legs? Where are they in relation, that mass to, how is a mass distributed in relation to her axes of rotation? And how's that going to impact how quickly she spins, so her angular velocity and her moment of inertia? And all the time you need to remember they've got this inverse relationship. When one of them's high, the other one's low. And that takes us back, if we have a look back up here, that takes us back to the fact that angular momentum remains constant. So it takes us back to the fact, because one of these is high and the other one is low, our angular momentum is conserved. So it is a bit complicated, and you are going to have to go over it a number of times just to make sure it makes some sense, but try and boil it right down, simplify it right down to what it is. Again, if you get asked a question on angular momentum and somebody that's rotating, it will be expecting you to define what angular velocity is. It will be expecting you to explain and define what moment of inertia is, okay? As well as obviously applying it, talk about what the athlete or the gymnast or whoever it is doing with their arms and the legs in relation to the axes of rotation. And then you might get something that looks a little bit like this. So this time we've got somebody, so whereas our figure skater was going around her longitudinal axes, we've now got a gymnast going round their transverse axes, doing some sort of backflip. So there's the start of the turn, there's the tuck in the middle, and then they open back up to land again. So we've got, let's just write that down there, start, tuck, open out to finish, and control the landing. Oh gosh, am I writing on this? So you might be asked to explain or label something like this. So if we look at A, this isn't the floor, this here is the line. So if we have a look at A, because it stays the same all the way through the turn, that one is obviously going to be angular momentum. So angular momentum stays the same because air resistance is negligible. Angular momentum is conserved, doesn't change, it stays the same. Once we've given ourselves a torque, a turning force, angular momentum remains set constant. That's why it's a straight line. You then have to weigh up what B and C are doing. And really what you need to do is say to yourself, right, okay, if we look at this picture in the middle here, we can see that they've got their mass close to their axes of rotation, and we pretty much know that during the tuck they will be spinning fast. So really this line here that's high indicates that C is more than likely going to be angular velocity because it's high in the middle when they're tucked up. If we trace that line down, it then wobbly line, it then goes down, it lowers as the body opens up, and they're now starting to spin slowly. So we can confirm that line C is angular velocity. Line B, on the other hand, so remember, if we know that they are spinning fast here in the middle, if angular velocity is high, something else must be low, and the something else is going to be our moment of inertia. Okay, and to confirm it, if we have a look here, this line here increases as they open out, as they move the mass away from the axes of rotation. So that just confirms that B is moment of inertia. You could be asked to apply that, and I'm just going to talk you through it. So if you're making notes, you might need to pause and stop as we go through. But if you were asked to maybe look at that gymnast who's doing that kind of back tuck somersault, you might have to explain what's going on at the start and the middle and the end. So if we have a look very quickly at the start, they'll have already applied a torque, a turning force. They'll have given the body a quantity of angular motion. We can see at the start, because their arms and the legs are away from that central axis of rotation, that their moment of inertia is going to be high. Remember, line B was moment of inertia. And they're going to be at this point spinning slowly. And the reason they're kind of spinning slowly is they've needed to have their arms and the legs out to give themselves enough kind of motion to get the height in the air so they can then complete that spin. When we look at the middle, they tuck their body in, so their arms and the legs come much closer to the axes of rotation. That means moment of inertia is low. They're quite happy to spin, but their angular velocity is high, so they're rotating very quickly. In terms of evaluation points or analysis points, this is really important because when they tuck up and spin quickly, it increases their angular acceleration and gives them enough time in the air to complete that move aesthetically to get a high tariff score. They then need to, if we start to look at the final picture here, as they start to open back out again, their moment of inertia increases as their arms and the legs move away from this axis of rotation. They start to slow down, their angular velocity decreases, and this allows them to control, or allows them to get into a position to control their landing and either have a nice spot landing or a nice controlled landing, or if it was a diver, a nice clean entry into the water. And all the time this is going on, remember, angular momentum remains constant. You're changing, if one of these changes, if one of these goes high, the other one goes low. And that allows them to complete a fluent and controlled aesthetic somersault. So go back and make some notes, have a look at the Padlet. Now I've explained it to you. Practice some of the questions that have been up before. And if there's anything that you're stuck on, just give me a little message on Teams.